Macy Huston. I'm sort of a fifth-year grad student at Penn State in astronomy, as you may have guessed from my background. But I just successfully defended my thesis last week, so I've gone ahead and assumed. I don't get my diploma and start my postdoc until August, but I'm still going to call myself Dr. Huston now. So I'm going to be talking about something that was not in my thesis. So I hadn't thought about too much for a couple of months, but I'm getting back to it now. This is some work I'm doing as part of the Penn State Extraterrestrial Intelligence Center. And this work is actually being led by Dr. Sophia Sheikh at the SETI Institute. So this project came out of a group collaboration called Characterizing Atmospheric Technosignatures, or CATS, which I'm very glad we found a good abbreviation for. And so what this group is doing is just kind of creating a library of possible technosignatures, and especially focusing on atmospheric technosignatures as JWST launches, and we're making a lot of advances in our ability to characterize exoplanet atmospheres. But this project we're talking about today actually goes a bit more broad than that, and we're thinking of all the technosignatures that we produce here on Earth. So the project we're calling Earth Detecting Earth is establishing benchmarks for detectability based on how strong our technosignatures we produce here on Earth are, and how far away you would be able to use our telescopes to successfully detect our technosignatures. So this is a very preliminary version of our plot here. We're going to have more technosignatures than this, and we still have to finish up a few calculations to get all our distances right. But we're basically just trying to calculate the detectable distance for our telescopes to observe our technosignatures for all of the technosignatures that we could think of that humans produce. So this is related to a similar concept called the Ignoscale, which was proposed by Socas Navarro et al. A couple years ago. This term is defined as the relative size or intensity of a technosignature in units of the same technosignature as produced by Earth's technology. So kind of the first step in our project is to quantify the strength of Earth's current day technosignatures. And this is kind of defining the power level. That is an Ignoscale value of 1. And then we're going to determine what distance we can use our technology to detect those technosignatures, and to keep things kind of uniform among all the technosignatures we're looking at. We're adopting a signal-to-noise ratio of 5, but we're also going to talk a bit about scaling relations you can use if you want to get higher signal-to-noise or something like that. So I'm just going to go through a few of our calculations here. I don't know why it's covering my word. Oh, well. So the first kind of technosignature I want to talk about is intermittent celestially targeted radio transmissions. So the types of signals that would produce this are MEDI signals, so intentional messages that we have sent out ostensibly to communicate with extraterrestrial life, but we don't really do a lot of that. So the more common types of signals we send out are powerful radio signals targeted at planets and asteroids in the solar system in order to characterize them with radar. So for our calculation, we are assuming that our radar transmitter is Arecibo, RIP, but our observer for our radio observations, we are using the currently under construction square kilometer array. If we assume an observation time of 1 hour, then we get our Earth detectable distance of 12,000 light years for our most powerful radio signals. So this is the highest number that we're going to see in terms of our distances here, but I wanted to start with it to really emphasize that I see technosignatures as a really important part of the search for biosignatures, because when you think about all of the signs of life that we produce here on Earth, our radio signals are by far the most detectable thing that we produce. So I really hope that the fields of biosignatures and technosignatures can work closely together, because I think we want to take as many approaches as possible to find any types of life we can in the universe. So the next category of technosignature is just another type of radio signal, intermittent celestially untargeted leakage. So these are signals that we intentionally send into the sky, but not necessarily with the aim of going to space. So things like military and commercial aircraft radar. We're just kind of assuming these standard aircraft radar systems for a transmitter, and again, observing with the square kilometer array. And our Earth detecting Earth distance is a bit over 200 light years. So this is still a pretty big distance. This includes quite a number of stars. If we're considering, the stars within this distance range. The next technosignature I want to talk about is persistent omnidirectional radio leakage. So there was some early work done on this topic actually in 1989, where Sullivan et al. Simulated the output of Earth's television tower transmissions as you might be able to observe them from space, and concluded that it's possible that other life out in the universe knows that we're here. Our TV signals aren't quite as powerful now as they were in the peak time, but we've got all kinds of mobile cell phone towers all over the world now. So there's a really great paper that just came out a few weeks ago by Mira Said et al. That kind of does a similar calculation to the Sullivan paper, but using mobile phone towers instead of television. So we adopted their value of a transmitter strength of 4 gigawatts, and again, using the square kilometer array as our radio detector, and we got a detectable distance of just under a light year. So this is a little bit too short of a distance to reach any nearby stars, but it's getting pretty close, and as radio technology improves, this kind of thing is going to become more feasible. The next technosignature I want to talk about is intermittent targeted laser leakage. So these are laser signals that we happen to be sending out into space. So for the non-astronomers in the room, the example that I want to use here is adaptive optics lasers. Adaptive optics is an astronomy technique where you take ground-based telescopes and distort their mirrors in order to account for the effects of the atmosphere on the light that we observe from space. There are kind of a lot of factors that goes into that, but one thing is that sometimes we need to create an artificial guide star to calibrate these. And so what we do is send really powerful lasers shooting into the atmosphere so that some amount of that laser power hits the atmosphere and bounces back for us to observe, while a lot of that laser power just happens to go out into space wherever it's headed. So for our calculation for laser leakage, we use the Keck 10-meter telescope and its adaptive optics system, and we get a detectable distance of about 10 light years. So this distance does include a few nearby stars, but it's important to note that we're not actually directing these lasers at any nearby stars because you only need to use adaptive optics, the laser artificial guide star, if you don't have a real well-known bright star you can look at. So we're never really doing that right at nearby stars, which would be pretty bright. So the next category of technosignatures I want to get into are exoplanetary technosignatures that you might detect, for example, in the atmosphere of a planet. So we've got an example here of one possible atmospheric pollutant, which is nitrogen dioxide. And this is based on work done by Kaparapu et al. A couple years ago. So this simulation was performed using the planetary spectrum generator and assuming that our observer is LUVEX, which I guess is now called Habitable Worlds Observatory, which is a space mission that's under development, but is a combination of LUVAR and HabEx mission concepts that was for a few months called LUVEX, but now this is already out of date. So our detectable distance here is a little over 3 light years. So this includes some nearby stars. But it's important to know that NO2 can also be created through natural means. So there's a lot of complicated chemistry at play here to determine whether it's actually artificial. But a really important thing about these spectral atmospheric pollution signatures is that you can use the same observations to search for technosignatures and biosignatures when you're looking at these spectra. So I think it's a really great way that these two techniques can work together. And then the last technosignature I'm going to talk about is city lights. So I'm showing a picture here of Earth as each part of the world appears at night with city lights. So for this calculation, we're using some work done by Thomas Beatty, where he assumes that our lights are primarily from high-pressure sodium lamps. In this simulation, our observer is LUVOIR-A, so a slightly earlier version of the LUVEX I talked about last time. LUVOIR-A was an earlier mission concept for that. So this exact design is not going to be launched into space, but we're going to have something similar. And our distance for this one is only 0.075 light years. So this means that we could only use something like LUVOIR to detect our city lights if we're in the Oort cloud, which is just kind of the outer regions of the solar system. So if you want to detect this kind of thing, you're going to have a planet that has a lot more lights than we do. And so I'll just kind of leave up my summary slide here as the list of the technosignatures that we're looking at. The first few on the list here are the ones that we quickly went over. I've got a few more highlighted in yellow, and for those, our calculations are still underway. And then we've crossed a few out that turn out to be technosignatures we've crossed off of consideration for various reasons, mostly because it's just not feasible to observe them from space at all. We'd be talking about still in Earth's atmosphere for our distance, or because another possible technosignature is observing the contents of Earth's atmosphere over time and how it changes. But we decided for this project that we're not going to get into things that are based on changes over time, because this is already a really big paper as is. So yeah, I can take questions. I also have my email and Twitter up there.
All right, thank you, Macy, our new Dr. Huston. Unfortunately, we only have time for one question, so I want to see some real enthusiasm.
Hi, thank you so much for your talk. I definitely agree with you that technosignature and biosignature scientists need to work more closely together. I was wondering, I know the paper is already super cool as it is, but as a sort of follow-up, would it be possible to estimate what sort of technosignature, like how those technosignatures would evolve in the future, and if there's one that's going to shoot up, and at what point in our future would we be detectable to most terrestrial planets in our galaxy? Or, I mean, we're like
yeah, we'll talk a little bit about that in the discussion, but we're not going to get too quantitative. But that is something that comes up, as in, you know, one of the main things you hear people talk about this in is like radio leakage, because like if our cell phone towers were more directed, you know, down at the Earth, they could be more efficient, and maybe more advanced technology has less leakage into space just because it's a waste of energy. So yeah, these are things we think about. I don't have any definitive answers right now.
Cool, thanks.